So we're looking at x squared plus y squared. We talked about it being the paraboloid. These are what we call cross sections. And this is a graph we've seen before. So there's our paraboloid, and we can see if we look down the YZ plane, we see our parabola, and around down, there's the XZ plane, we get our parabola. That's called looking at cross sections of the graph, zeroing out one of the variables to make it a little bit easier to look at. Okay. Now, this is the plot of the function e to the negative x squared plus y squared. Anytime you see one of those x squared plus y squareds, you're going to see something circular going on in the graph. So basically, this graph looks a little bit like e to the negative r squared, or e to the negative whatever our variable is squared. There's our exponential look there. But this x squared plus y squared term is what creates this roundness. So whenever you see an x squared plus y squared term, you can look for some kind of circular symmetry. So these are just things that we look at. All right. Now, here's a graph that I want to take a look at. Z equals the square root of 4 minus x squared minus y squared. Now, because we're still new to this stuff, we may not recognize something like this right away. But imagine if you squared both sides and added the x squared and y squared over to the other side. What would that be the equation of? Sphere. Circle in 2D, but a sphere in 3D. Now, the square root does have an effect on this thing. So let's take a look at this graph. We get the top half of a sphere, and that's because of the radical. There's no way to get negative z values. Now, a sphere is not a function because we can only get one output per input pair. So the half sphere is actually a function. Now, we're still going to plot spheres, but by definition, it's not a function of x and y. So we just get the top half of a sphere as a single function. Now, one of the things that we're going to start doing is setting our function of two variables equal to inputs. For instance, 0. Okay, maybe that wouldn't be that interesting. That would be that circle in the xy plane. And then we start to think about it for other values as well. So 1 or a half or 3/4. So we start to look at the 3D plot for particular outputs, because what that does is that creates functions of just x and y, which in 3D are just lines, as opposed to a whole surface. All right. These are called contour lines or level curves. This is not most likely not going to be a brand new concept to you, but you probably never called them contour lines or level curves. All right, this graph is what we would call a contour map. It's a topographical map of a 3D image. So we want to start to think about, well, gee, what's going on at some of these places, right? Yeah, each line has the same height, right? So the closer two lines are together, the shorter the run for the exact same rise, which gives us a larger slope. This one where it has the smaller circle probably has a sharper peak than this one. And here's the 3D image from the side. So they were peaks in this case. Without knowing the value of the level curves, we couldn't say if they were peaks or valleys, but we can see clearly, okay, so they were peaks. Notice these marks here, 500, 1,000, 1,500, 2,000. Those are the values of the level curves. Those would be like the Z values for each level curve. Anytime we draw level curves by hand, we want to mark the Z value because we want to know, hey, is this thing going up or down? Is it increasing or decreasing? The other thing I'll point out about those contour lines, notice that the values are equally spaced. All right. We'll always want to use equally spaced values, and we'll talk about that as we look at a couple contour plots. But that's how we can tell, as Mark was pointing out, how quick it's going up or down, because then all we have to do is look at how close together the lines are. If we don't equally space the value of those lines, we lose that guarantee. We lose that that visual aspect. So we'll always equally space our contour lines. They separate lower elevations from higher elevations. The closer the lines appear to one another, as Mark said, the more steeply the surface inclines or declines, depending on if it's going up or down. Again, contour lines, level curves, I'll use those terms interchangeably, feel free to. All points on any given contour line are at the same height. Contour lines corresponding to different heights can never cross. Why not? That could be a possible explanation of it. But think about what would happen, right? If we had two contour lines crossing, that would be saying you have two different heights at the same input, and that breaks down our function definition, right? We want to know if we're at point XY, what is our height? And like Andrew was saying, we're taking a bird's eye view, so even an overhang, it would give us the higher of the overhang. Okay, now one of the very cool things about CalcPlot 3D, it will do contour plots for us. So this button right here will create a contour plot. We don't need a level at -1. Like we said, we can't get any negative Z values. We'll do a step size of 0.2. Let's do 20 level curves. There's a whole bunch of other cool stuff you can do on here if you guys want to play around with it. And create plot. There is our contour plot. Now remember what we said earlier, these contours are equally spaced. In fact, they have a step size of 0.2. They're all 0.2 apart in the Z direction. So when we see them close together, well, that's the steeper part of our hemisphere, and they get further and further apart as we get towards the peak. Now we're going to start talking in terms of calculus, or as we get towards the maximum. Okay, remember one of the things we did in Calc 1 was optimize, right? Maxes and mins. We're going to do that in 3D. Now we can start to identify it from a contour plot, because if we see these concentric circles, where the circles are getting further and further apart, we know we're getting to something that bottoms out or hits a peak. The other cool thing is if you click on this, you get a plot of your 3D image along with your level curves. So you can see when we look from the side, you can see how those red lines are equally spaced. But then when we look down, that's when we get the concentric circles. So CalcPlot 3D is a great tool for looking at level curves. Okay, a couple things I want to talk about with regards to level curves. This is just the definition. Don't worry about the definition. I just want you to know what they are and how to use them. All right, so we want to talk in terms of calculus. As long as we're moving in a direction that is tangent to a level curve, so at any given point, as long as we're moving tangent to the level curve, the height doesn't change. Now, remember what we're talking about when we talk about a tangent line. Obviously, if you follow this black line, eventually you're going to be off of that level curve and your height does change. So we're talking about an instantaneous moment, right, with a tangent line. So these tangent lines move along, will change direction as we go along this height. So it's going to be a really important idea moving forward. As long as we're going tangent to a level curve, our height or our Z value is not changing. Now, if I'm at a point and I want my height to change as quickly as possible, either up or down, what direction do I want to move in? Normal. I want to move normal to the level curve, or perpendicular to the level curve, or orthogonal to the level curve. That concept keeps coming up again and again, right? So important that we have 3 different words for it. So moving perpendicular, there's another word. Moving perpendicular to the tangent line or to the level curve is going to be what we call the direction of steepest ascent or descent, depending on if we're going up or down. Again, when we start talking about partial derivatives, directional derivatives, that's going to be a key concept, but you guys already have an understanding of it, right? If you want to get to the next level as quickly as possible, you want to move in a 90-degree angle from where you're at, or your direction of motion. So that idea of perpendicular is going to continue to be really important for us. Let's take a look at a linear function, what its level curves look like. So 2x plus 4y minus 2. All right, the all exciting plane as a graph. Well, remember what makes a plane? A constant rate of change. So what does that mean as far as our level curves? Let's put a few more in there so we can see it a little bit better. We get level curves that are equally spaced. Again, it's still a little hard to see. Let's move them out a little. There you go. Notice that the level curves for a plane are always going to be parallel lines, okay? That's how you can recognize a plane from its contour plot. They're just perpendicular lines. Why? Well, because we have a constant rate of change. That's going to keep them all parallel. Okay, now we need to extend these ideas a little bit. Imagine a temperature at a point in space. Well, it takes 3 inputs to determine a point in space, and then the output would be the temperature at that point. So what this introduces is what we would have as a function of 3 variables. All right. We don't have the ability to plot in 4D. So when this happens, we can no longer plot the entire function. So this function t equals x squared plus y squared plus z squared. We're not able to plot that. So we're forced to deal with what are called level surfaces, which means we do the same thing we did to find level curves. So to find level curves, you set the output to equally spaced constants. Level surfaces, you set the output to equally spaced constants. Okay, so x squared plus y squared plus z squared equals 1 would be a level surface of this function. Now the level surface can be plotted. This is, not a new one for us. This is just our sphere of radius 1. But the big thing I want us all to take away from this, oh, sorry, that needed to be done implicitly. So that is a level surface of our function of 3 variables. We are not able to plot a function of 3 variables. We don't have the 4D to do it. These are what are called level surfaces. This is another idea we are going to leverage next week when we're looking at some tangent planes. There's nothing crazy going on here. Basically, if your function has 3 inputs, it's basically a 4D function because 3 inputs plus 1 for the output. And so we can only look at level surfaces. Now, if your function has more than 3 inputs, there's no way to visually represent the function. So what we're doing is we're taking a look at what we can visually represent, using that to build a lot of the concepts, but a lot of our concepts will apply to higher dimensions. All right, so we got level curves, now we have level surfaces. This next slide, again, is just the definition of level surfaces. I don't want you to be worried about the definition. All I care about is that you understand what they are. So the takeaways from this section, and we're gonna, we'll do a worksheet here in a little bit. The major one is the level curves or the contour lines, which is basically a plot of lines that represent certain heights on our function. It's a topographic, it's basically a 2D topographical map. That's what I want you to take away from that. We know that if we're moving in a direction tangent to a contour line, the height does not change. If we move perpendicular, the height changes as quickly as possible. And that the last thing is, if we have a function of 3 variables, we can plot their level surfaces. We're going to get a chance with the worksheet to kind of solidify some of these ideas. But any questions